Okay, so good afternoon. We are going to be starting with chapter number 2 today. The chapter number 2 also deals with combinational circuits. So, if you remember, I showed you this picture sometime in the last week. I'm going to show it again to you. Please let me know when my screen is visible.
Ma'am,
Ma'am,
it's
it's visible.
visible.
Okay, right. So, these are the type of combinational circuits that we had discussed. I had told you that the combinational circuits can be broadly categorized as being used in the fields of arithmetic and logical computations for data transmission and for code conversions. Right? Just give me a second, please. Is the screen still visible?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Right. So the combination circuits we said could be broadly categorized into three categories based upon where they are used. The first is that define usage for arithmetic and logical computations. The second for data transmission, and the third for code conversions. Okay. So under the first category, you've already visited the adders and the subtractors where we have designed the half adder and a full adder, half subtractor and a full subtractor. And now we're going to begin with chapter number 2 that deals with these combinational circuits. So we will be talking about the multiplexer, the demultiplexer, encoders and decoders. So your book talks only about multiplexers and not about the demultiplexer, but I'll be doing that with you as well. Okay, so we're going to be starting today with multiplexers first of all. So, just to give you an idea of what is a multiplexer, let us first talk about perhaps a term that you're more familiar with. Uh, what do you mean by a movie multiplex? There are multiplex complexes, right, where you go and watch movies. Are you familiar with that, students?
Yes, ma'am.
So, what happens there when you go to PVR cinemas and all? It's a single building wherein there are multiple screens, right? There are
Yes, ma'am.
multiple movies, one on each screen, and you can actually select which one you want to watch. Right? Is that right?
Yes, ma'am.
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am.
So earlier there used to be cinema halls with a single screen. Now I have told you this so that you can understand the literal meaning of the word multiplex. Okay, not that because this is akin to somehow the kind of multiplexer that we are going to talk about in digital electronics or the computer system architecture, but just to um invite your interest in the word multiplex, which is literally used in English to mean that multiple things are folded together into one. Okay, when we intermix multiple things together into one, it is called as multiplexing. Okay, so on similar lines, what does the multiplexer that we are going to study, what does this digital component do? It is an electronic circuit like our adders and subtractors that we had discussed, and What it does is that it basically gets multiple inputs and it selects one of those inputs and reroutes it to the output, okay, and switches it to the output. In the very basic layman terms, if I were to show you, please see, this is the block diagram of a multiplexer, okay. So this multiplexer is getting, let's say, some 2 raised to the power of n inputs here. You can see that. So these are the inputs denoted by I1, I2, I3 respectively up till I2n, right? So out of these, one of the inputs will be selected to be passed on to the output channel. Is this clear?
Yes, ma'am.
Yes,
Excuse
ma'am.
me, ma'am.
Yes, beta.
Ma'am, the input which will be selected, it will be any input depending on the multiplex.
Very good. That's exactly the question that I was looking for. So I said one of these inputs will be passed on to the outputs, right? The next logical question is that which input and how do we control that input? Obviously, to be able to control this circuit, we should be able to control this part of the circuit. Yes or no?
Ma'am, I didn't get it.
I'm just going to answer your question. So which of these inputs will be passed on to the output channel is specified with the help of these lines that you see here, which are known as select lines. Which are known as,
Select
Select
line.
line.
yes, okay. So I'll be discussing more about this with a very small configuration of a multiplexer. We will start with a very basic one, which is a 2 cross 1 multiplexer. A multiplexer is also known as a MUX or a data selector. Okay, so we will be talking about that in detail. The design will completely be, discussing the design of a 2 cross 1 MUX. But let me first ask some student to help me by reading the text on the screen. So who is going to read for me today?
Dipali,
Dipali. Right. Thank you, Dipali.
you're welcome, ma'am. Shall I start?
Yeah.
The term multiplexer is derived from the word multiplex, which has a Latin origin. A multiplexer is a combinational circuit that is designed to switch one of the several input lines to a single common output line by the application of control signals. The selection of one input line from amongst the multiple inputs is facilitated by the separate input
Is
lines
facilitated.
is facilitated
Yes.
by the separate input lines called the selection lines. Multiplexers operate like very fast acting multiple position rotatory switches connecting
Rotary
or control
switches. Yeah.
rotary
So
switches
please see, multiplexers operate like very fast acting multiple position rotary switches connecting or controlling multiple input lines called the channels. Means every input line is called a channel. And what does the multiplexer behave as? It behaves as a rotary switch. Rotary switch means a switch because it can switch from one input to another and form its liaison with the output, and to do so it has to be capable of rotating itself. Okay, so that's the internal hardware specification that we're talking about. It is like that. Okay, yeah. Multiplexers operate like,
Multiplexers operate like very fast acting multiple positions rotary switches connecting or controlling multiple input lines called channels one at a time to the output. A multiplexer is also therefore known as a data selector.
yeah,
Multiplexer attributed commonly as a
yeah.
MUX.
This we can leave out here. I've highlighted what is to be read here. Okay. So, when was the multiplexer invented? Uh, this isn't definitely in your book. Let's just read a line or two here. The origin of the multiplexer dates back to the late 1800s. It was first used in telegraph systems, which were ostensibly limited in scope and efficiency. इसके बाद में प्लीज देखिए थॉमस एडिसन invented something which was called as diplexing. So instead of multiplexing, diplexing, which allowed two separate messages to travel in the same direction at the same time. So it basically doubled the operations. So using the same line, two messages were sent instead of one. So which led to a double throughput and therefore was considered a breakthrough. Okay. Yeah. Rupali, yes, please read.
2 to the power n cross 1 MUX has 2 to the
MUX.
power n.
We call it a MUX.
MUX
Okay. Hmm.
Musk has 2 to the power n or less inputs, a single output, and n select lines. Select lines are input lines that
So
are
yeah, just
used.
a second. Yeah, just a second. Give me. So as we had looked at this block diagram, okay. So the multiplexer we say has some inputs and we take that as the power of 2 raised to the power, right? So if that is n, if the number of inputs is 2 raised to the power of n, then how many selection lines, my question to you is, how many selection lines will I require to be able to choose any one of these lines which can be passed onto the output line? Yes?
n.
Did I get an answer there? Who was this? Please speak up. Have you understood my question?
Yes, ma'am. Ma'am, can you repeat once again?
Okay. So have you first of all understood the role of the selection lines?
Yes, ma'am.
Role of the selection lines, as their name suggests, is to select one of the inputs to be passed on to the output. Clear?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Now I just told you that we always take the number of input lines to be some power of 2. Let's say I have 2 raised to the power of n input lines. Then I will call this multiplexer a 2 raised to the power of n cross 1 multiplexer. Okay? Because the output is always 1. Any problem?
No,
No,
ma'am.
ma'am.
Right. Now, my question, how many selection lines do you think will be required if there are 2 raised to the power of n input lines?
n.
10.
N.
And
That's right. Why?
Ma'am, one for each input line.
But there are 2 raised to the power of n input lines. Then why are you saying n select lines? You should have said 2 raised to the power of n selection lines.
Ma'am, I think their address bits will be in N.
Yeah.
Because each selection line will select from two input lines.
No.
Ma'am,
See,
because
we have already discussed that in order to identify one of the 2 raised to the power of n things uniquely, now those things may be the input lines, as in this case, or they may be the address locations, as we had discussed in the at the time when we discussed RAM, right? So, in any of these cases, we have seen that whenever I have 2 raised to the power of n things, out of which I need to identify one of them uniquely, how many bits do I require? N. बड़ा सिंपल है इसको देखना प्लीज देखिए if there were only two input lines, if there were only two input lines, okay, how many bits would I have required to select one of them? Only
One.
one,
One.
because I could have
And
called this as 0 and this as 1, right?
Yes, ma'am.
yes, ma'am.
If I had 4 input lines, then how many bits? 2,
Two.
Two.
because I could have called this one as 0 0, this one as 0 1 1 0, and 1 1. Yes,
Yes,
ma'am.
ma'am.
Yes,
Yes.
ma'am.
and so on so forth, right?
Yes,
Yes,
ma'am.
ma'am.
So how many selection lines then?
N.
N.
And
N.
Right.
N.
Yes, Dipali, continue from
A
here.
A 2 to the power n cross 1 must has 2 to the power n or less inputs, a single output, and n select lines. Select lines are input lines that are used to select one out of the 2 to the power n inputs of the multiplexer to be switched.
What happened?
मैम ये बॉक्स प्लीज हटा दीजिए.
Okay.
Yeah, it's fine. To be switched onto the output line. Accordingly, 8 cross 1 mask would therefore have 8 input lines, 1 output line, and 4 selection lines. Figure 1.2.1 summarizes this information in the form of a block diagram for a 2 to the power n cross 1 mask.
Is this clear?
Yes, ma'am.
Yes,
Right.
ma'am.
Yeah.
Where are the multiplexers used? Multiplexers are used in various fields where multiple data needs to be transmitted using a single line. Following are some such applications. Communication system. Multiplexers find wide deployment in communication systems such as computer networks, relay and
There
tributary
they are.
station,
Just read the highlighted part. Yeah.
where they are used to transmit different type of data such as audio, video at the same time using a single transmission line. Telephone
Okay.
network.
So the first and the primary usage of multiplexers, they find a very wide usage in the area of computer networks. What is done is that audio, video, they are multiplexed together and sent on a single transmission line. Okay. Yeah. Second,
Telephone network. In telephone network, multiple audio signals are integrated on a single line for transmission with the help of multiplexers.
yeah.
Third, computer memory. Multiplexers are used to in memory systems.
So basically, when they're used in memory systems, the number of wires which are required to connect the memory to the rest of the computer system or the circuit, they are reduced by using the multiplexers. Okay, and as we had discussed, lesser the number of wires, simpler the circuit, easier to debug, easier to understand, okay, easier to, and therefore whatever is easier to understand is easier to maintain, right? Yeah. Now let us start with the design of a 4 cross 1 MUX. So the first step definitely again is drawing the, for any combinational circuit, what is the first step of designing the combinational circuit?
Block
Drawing
diagram.
block
Block
diagram.
diagram.
Right. So a 4 cross 1 MUX can be drawn as you can see on your screen at the moment, right? We have 4 inputs coming in, a single output. And how many selection lines?
2.
Two.
Right. Now please see, so when we talk about the multiplexers, right, we don't talk about truth tables, but instead we use something called as a function table to describe the functionality of a MUX. Okay. Now, what is this function table? So as you can see here, this function table lists the value of the two selection lines. Okay. That means the binary combinations, the binary combinations of the input variables S1 and S2 that we can give them, and the corresponding input line that will be selected as the output. Okay, so this is not a simple 0 1 kind of a truth table that you see here. Okay, this expresses the output in the form of input only with the help of selection lines. Okay, this table expresses the output of this particular electronic circuit in terms of its input only, vis-a-vis each particular combination of the selection lines. Is this clear to everybody? Is this clear to
Yes,
everybody?
ma'am.
Yes,
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 ma'am.
ma'am.
yes, ma'am. No, ma'am, it's not clear.
Okay.
Can you please repeat?
So what is a function table and how is it different from a truth table? In the truth table, what did we have on the left hand side? I'm asking you,
I
what
mean,
did we have on the left hand side?
Inputs. Input.
We had the input variables, right?
yes, ma'am.
And on the right hand side, we listed the output.
Outputs.
Clear?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
But here, and the output was, in the truth table, the output was either a 0 or a 1, some Boolean value, right?
Yes, ma'am.
Yes,
But
ma'am.
in this table, as you can see, that kind of a table will not be able to describe the behavior of something which is known as multiplexer. Okay, it will not be able to capture its sense. Why? Because it does not mention the selection lines at all. Okay, it does not depict the output that we get in terms of the input that we are giving. What are the input variables here? What are the input
I1,
variables
I2,
here?
I3.
Yes. So ideally, if this were a truth table, then I should have had input variables at this side, right? Okay. But I will not be able to describe the function of my multiplexer using that kind of a table. Let us see why. So for that, let us see what does this multiplexer actually do. So as we had just discussed, when the value of selection lines will be 0, 0, then the input I1 will be selected and that will be passed on to the output. When the selection lines have the value 0, 1, then I2 will be selected and passed on to the output. 1, 0, I3, 1, 1, I4. Is this clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
So
Yes,
you
ma'am.
can see that I cannot capture and put this functionality via a truth table. Yes or no? Isn't it
Yes,
better?
ma'am.
Isn't it better? Or let me put it this way, please look at this table and then you can decide for yourself and let me know. If I put it this way, if I put instead of the input variables, if I put the selection lines here and I plot their values here and put the corresponding input variable as the output, isn't it more reflective of how this multiplexer is working?
Yes, ma'am.
We see that when
Yes,
S1, S2 are 0, 0, then I get I1 as the output. When 0, 1 is given as the selection lines, then I get I2 and so on and so forth. Doesn't this table describe the exact behavior that I used so many lines to describe to you,
Yes, ma'am.
Yes,
Yes,
right?
ma'am.
ma'am.
So that is why we use a function table instead of a truth table. We call it a function table. Why? Because it depicts the function of a multiplexer. How is it functioning? Okay, is this clear?
Yes, ma'am.
Yes,
yes,
ma'am.
ma'am.
Yes,
Excuse
ma'am.
me, ma'am.
Yes.
Ma'am, Akshita Khandelwal here. Ma'am, I just wanted to ask that function table is basically helping us to know that which will become our input.
Which input will be selected?
Which input will be selected? Yes, ma'am. I'm asking that function table is helping to tell us that which input will be selected of all the inputs that we are giving to MUX.
Yes, to be passed on to the output. And this is the job of a multiplexer,
Okay, ma'am. Thank you, ma'am.
right? So now from this function table, we can directly draw out a Boolean expression for the output variable O. We see here. So you can see that O is equal to, we say that either I1 is 1, please see, I1 is 1, and
Excuse
at
me,
the
ma'am.
same time, yes,
Ma'am, you said that a mux, the function of a mux is to is that it can pass on multiple signals on the same line, right? So, ma'am, but in this, ultimately only one of the inputs is being selected and passed on to the output.
yes, that's right. That's right. But this is, see, you will also do this concept later in networks. Okay. So there you will be talking about different types of multiplexing. One of the example, for example, you will be talking about frequency division multiplexing, which is known as FDM, or TDM, which is time division multiplexing. Okay. So what happens is that not it is not always the case that all the input sources are using the channel at the same time, the transmission channel at the same time. Is this okay? Is this clear?
Yes, ma'am, got it.
Right. So what we can do is, instead of devoting a dedicated channel to each source, we can multiplex. We can, that means we can connect them all to a single transmission line. Okay. Now, if you can see that if it is a 32 cross 1 multiplexer, how many savings it can give me? Clear? Is this clear?
Yes, ma'am.
Okay. Otherwise, laying down so many dedicated lines and maintaining them when all of them are not being used at all times isn't very practical,
Okay, ma'am.
right?
Yes.
Okay. So you will be you will be learning about these concepts called frequency division multiplexing, time division multiplexing. When we talk about time division multiplexing, uh, chunks of time, you know, are divided and given to each source. Okay. When we talk about FDM, that is the frequency division multiplexing, different frequencies uh, are taken together, and at one time, one of them is sent through data. Is this clear? So these are advanced concepts as of now, but you will be learning about them later in detail when you do computer networks. There is a complete paper on that, right?
Okay, ma'am.
Okay. So now what do we wish to do next? We want to get what is the next step? The next step is to get a Boolean expression for the output variable, right? So for O, we want to get a Boolean expression. We can see that when S is equal to 1, when S1 is equal to 0 and S2 is also equal to 0, but I1 is 1. Now, what do we mean by saying I1 is 1? That means there is some data on this channel which is to be transmitted. Okay. So we recognize it as a high. Okay. So what happens is that the uh, button corresponding to the Boolean button corresponding to this input variable will be set to 1 by the user. Okay. When there is data on this channel, right? So when these two variables are 0 and I1 is 1, right? This you can see as the first Boolean condition. Can you see this here?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Right? Then the output channel has to be activated, right? Okay. Or when this is 0, this is 1, and this is also 1, which you can see in the second Boolean expression. Can you see it here? Is it too small for you to see? The font is okay?
Yes, ma'am.
Yes,
Can you
ma'am.
make out? Can you make out? Right? I've increased the font.
Yes, ma'am. We can see.
Right. Or when S1 is 1, S2 is 0, and I3 is 1. Expressed like this. Okay. Right? Or these two variables are 1 and I4 is also 1. Okay. If any of these conditions is true, then the output is true. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
This is how we can express the output variable in the form of this Boolean expression. Okay. And after that, what do we need to do now? The last step, that is drawing of the circuit diagram.
Ma'am,
Okay. So this
uh,
has no complexity. As you can see, it is simply, implementation of the Boolean expression that we have derived. So S1 dash S2 dash I1 S1 dash S1 के आगे negator लगा दिया, S2 negated. All right, all these are connected to a 3-input AND gate. Okay, and similarly for all these Boolean expressions, we have uh, one AND term, one AND gate here in the logic diagram, all of them going to a OR gate. All of them going to a OR gate. Okay, giving us the output O. Giving us the output O. Is this clear to everybody?
Yes, ma'am.
ma'am,
Excuse me, ma'am.
Yes.
excuse me, ma'am.
Yeah.
Ma'am,
Why are we doing this? Like, why are we doing it this way? Like, first we are
Because
adding
this is not a truth table. We are deriving the Boolean expression from a function table.
Ma'am, how did we derive it? That I didn't like understand properly.
But
How?
we
Why?
have not, we don't need to derive it only. We can simply see it from the truth table. Can't you see it from the truth table? I've just explained it. Every row I've explained.
Mm,
O, please see the what is the output of this entire function table?
the inputs only.
It has to be activated. When does this circuit work? When either this combination is activated or this is activated, right?
Okay,
Or
ma'am.
this is
Got
activated
it.
or this is activated, right? You can see this in this circuit diagram as well. So when ye- the, it is the same thing that I'm putting in the circuit diagram also, na? Yes or no?
Yes, ma'am. I got it.
Got it now? Okay.
Yes, ma'am.
Excuse me, ma'am.
Yes.
Ma'am, I want to know, you said that there is a value of 1. I1 is 1 because of some data. So, ma'am, there is always some value, some data in all the inputs. So, all the inputs are 1.
See, uh, again, this is something that you will learn later. Okay. As I told you last time, there is it is never that there is no charge on a wire. Okay, so when it is connected, power is being supplied. But whether we have to consider the charge or for the in the context of what we are talking, whether we have to consider that boolean 0 or 1 as our data, whether we have to treat that as our valid data is what we need to see, and several mechanisms are used for that. Okay, so sometimes there is a data valid line, okay, which is used uh, to indicate that uh, uh, to a circuit, that the circuit should now take cognizance of this particular input. Okay, is this clear? So
Okay, ma'am. Thank you.
in our case, you can think of these I1, I2, I3, I4s as Boolean variables, okay, or switches to denote that when a particular channel is getting information which is to be passed on to the output. So when the signal has to be given that this line contains valid information, then I1 will be set to 1. Otherwise, it will be kept at 0. Is this clear?
Yes, ma'am. Thank you.
Yeah.
Ma'am,
Yes.
ma'am, why is it so that when first selection line and second selection line both are zero, first input line is passed on to output, not second, third, or fourth? Is there any logic behind this?
Beta, uh, see, there is no harden. If I don't think what you are asking is what you want to ask, I'll just correct me if I'm wrong. What you want to ask is that can we interchange these? That means can I put I3 here, make it I3 here, and I1 here? Is this what you want to ask?
Ma'am, I'm asking why when first selection line is zero and second selection line is also zero, then how do we know that first input line should be passed on to output?
Yeah. And what have I said? Just see
Um,
on the screen. What have I done?
yes, ma'am.
Is this what you want to ask?
Yes, ma'am.
Right? So basically, there is no hard and fast rule. There is no hard and fast rule which says that, for the 0 0 combination, I must select I1 only and not I3 or I4 or I2. Okay? There is no hard and fast rule. Okay? But to keep it simple, to keep it simple, the first possible input combination of these two select lines. What is that? That is 0 0. Yes or no?
Yes, ma'am.
We associate it with the first channel, with the first input channel. Okay?
Yes, ma'am.
Then the second one with the second one. So all this goes into saying that, again, that same line that I repeat again and again, easier understandability means easy maintenance, easy debugging. Okay, so it is good to follow some conventions. Clear?
Yes, ma'am.
Right?
Yes, ma'am.
And please see that uh, this is off the record, very informal. I wish to quote this, but in the theory exams or even in your Viva, you should stick to these combinations only. Though I am again reiterating that there is no hard and fast rule that binds us to say that this particular input variable should only be selected with this select line combination. Okay. Physically, if I place I3 on the top and I1 uh, uh, down, then whatever is the first input channel can be passed on to the output whenever I give 0 0 for the selection lines. Okay. But for your examination point of view, I request you to stick to the textbook format. Okay. The idea is that generally answer key is prepared, or some teachers may just fall back upon the textbook or conventional way of treating a particular circuit. Okay, this is the conventional way, right? So they may not, drag themselves this far to justify you, uh, and you may lose out on some marks. Is this clear?
Yes, ma'am.
Okay, so I'll stop here for the day because if I start the next topic, we will not be able to complete it. and the discussion would be futile. So I want to discuss next time a quadruple multiplexer with you. Next time I'll discuss that. We will do that from the book itself. Okay. Meanwhile, I want you to revise this when you come to the next class, because this discussion is going to be extremely instrumental for our next lecture, which will be on the not just upon the designing of a little complicated multiplexers, where we will be talking about how to construct a bigger multiplexer using two smaller multiplexers, and integrating multiple multiplexers into one. So I'll pass on the recording of this lecture to you just after the lecture so that you can revise. Please also make it a point to go through your textbook. Reading your textbook is very important, and no teacher, no book, no video, no other resource in this world is as good as, going through a good book for a particular topic. Okay, so for a full comprehensive understanding, you should always at least follow your textbook, more if you have more books. Okay, this is my request to you. ठीक है बेटा? I'll be sending you the attendance link. Please mark your attendance before you leave.